In this notebook, we're just going to start taking it up an extra level. We're going to get a bit more complicated, and we're going to be moving from the kind of intermediate Python to the slightly more advanced Python. So again, don't hesitate to ask questions and interrupt me whenever you want. Okay, so what are we going to cover in this notebook? So we're going to look at inheritance. So this is really, kind of core concept to object-oriented programming. And we're going to look at composition, which is something that's a little bit less known, but I found extremely useful in my own personal work. And then finally, I've got let's say the most complicated thing that we could possibly talk about today, which are abstract classes. So we'll only get to that if we have time. We're going to focus on these first two and see how it goes. Okay, so as usual, we're going to start by setting up our notebook, making sure we're all set to go. For this case, we just need this print error function. And we can go straight into inheritance. Okay, so when we were talking about object-oriented programming, we mentioned several concepts. So we already looked quite a bit at encapsulation. We looked at these like calculator examples and this Newton example where we kind of encapsulate similar information into a well-structured class. We talked about maintainability by like having easily well-defined functions that do one simple thing, and then kind of a hierarchy of using those, which means it's easier to debug each one of those functions independently, and we only need to fix it once to fix the entire code, right? So we avoid repetition of code in various different places. We avoid redefining things and so on. So another thing we talked about was reusability, right? So one of the best ways to kind of take advantage of reusability in object-oriented programming is by using inheritance. So not only can we like reuse functions for multiple purposes, we can actually reuse classes for multiple purposes, right? So basically writing a class that has features that are useful for other classes is a really good way to abstract your code. So if you notice some properties that a lot of classes are using, why not abstract them into a parent class that can then be distributed down to the child classes? And then you improve this maintainability and reusability of your code, right? If you only need to fix one part of the code to fix everything else, it's much easier. Okay, so let's see how we do this in Python. Okay, so we're going to start by defining a parent class. So in this particular example, the first thing we're doing is defining just a normal class. So I'm calling the class parent, but it could be called anything you want. And there's nothing special about the way we've defined this. So simply calling class parent, we're defining one static method. You already know all about static methods for addition, right? So we can look at the dictionary of the class in the usual way, everything as expected. Secondly, we can define a child class. So this class is very similar to the previous one. We have a definition of the class, we have a static method and the dictionary and so on. But notice that we have added something here, right? So basically after the name of the class, we've added round brackets and the name of the parent class. So basically this is the point in which the class realizes that it's doing some inheritance. So it's basically saying, child, I'm inheriting the properties from parent, right? If we look at the dictionary, nothing special. But if we wanted to know what classes the child is inheriting from, there's another hidden variable called bases that we could look at. So if we look at child.bases, yeah. Because it's not part of the child dictionary, it's part of the parent dictionary. Because what does it mean inheriting then? The inheriting is a hierarchical pointing. So imagine, you remember when we were talking about the difference between instances and the base classes, right? So we had the base class dictionary, and when we create an instance of that, we get a unique dictionary, and that instance can point to the base class dictionary or its own dictionary. So the same thing with inheritance. So imagine you have an instance of a child class. It points to its own dictionary, its base class dictionary, and then to its parent class dictionary. So there are 3 dictionaries now in the chain that it can point to, and it has the same hierarchy. So if I look for attribute, my attribute, if it's not in my instance, I will look into my direct class, which is the child class. If it's not in the child class, I'll look into the parent class. And if I don't find it in the parent class, then I will raise an error. Yes, yes, it will work. Yeah, and I'm going to demonstrate that in just a moment. So here I just wanted to show you that you can find out who the parents are, right? So basically this basis is kind of looking at the DNA of your child class. It's like, who are my parents? Well, I can tell you who my parents are. Now, again, this is a hidden method because in most cases, if the code is well written and well documented, you shouldn't have to look up who the parents are from an instance. But you never know who's written the code or whatever, and you might get lost as to where some attribute is going. You have an instance and you have a method that you can call, but you have no idea where it's defined. I've looked in the base class, I've looked in the instance dictionary, I can't find it. And you look at the bases, you're like, oh, there's a huge hierarchy of parents in here. Maybe in one of those, that method was defined, right? So this might help you, debugging somebody else's code or something like that. Okay, so here we go to Valeria's question. Child.add, child.subtract. So the child has access to both methods, right? So if I remember correctly, add was defined in the parent and subtract was defined in the child, but the child has access to both methods, right? Because of the hierarchy, the child can look at the parent's methods. Okay, so let's have a look at another example, right? So it doesn't have to be a method, right? It could be any attribute. So in this case, we're defining a parent class with the attribute x equals 1 and a child class that shows the value of x. And you can see it works, right? So the child is able to find the attributes that belong to the parent. So now we have the same thing that we had with the difference between the base classes and instances. If we have an attribute that exists in the class dictionary and we redefine it in the instance, it's going to override the default definition from the class dictionary. So basically, we'll always go to the lowest level in the hierarchy. So if we have a parent that has x equals 1 and we define a child with x equals 2, when we run show, it's going to find its own value of x, right? It's going to override the parent, right? Define children. Okay. And this works completely hierarchically. So we could define a grandparent class and a parent class and then a child class, and then they hierarchically inherit from each other. You can see that the child has access to its own value of z, its parent's value of y, its grandparent's value of x, but the name has been overridden at each stage. And so that the final name, the final definition is the one that gets used, right? So again, this is important to know how it works. And I would say now, again, for best practices point of view, it's really bad to override parent attributes, right? So if you have an attribute that you have to override, it probably shouldn't be in a parent, right? So essentially, imagine you have a method that you want to distribute to your child classes. If you have to override it in all of the child classes, it probably shouldn't have been in the parent class in the first place, I would argue, right? Because the thing is, what you're adding now is really hard for somebody who hasn't written this code to debug it. Because if you have the same method defined 10 different times and on a hierarchical chain, it's pretty hard to figure out in which case the bug arose. You're like, hang on, which one am I looking at? And the fact is that, like, if I have to redefine it at each time, that's probably the level at which it's being redefined is probably the level at which it should be defined in the first place. Now, that's a kind of, rough rule of thumb, right? Now, of course, you can find exceptions for anything, but I would just say in general, if you have to think about it, probably best not to override unless it's absolutely necessary. Of course, if somebody else wrote the parent class and you're writing the child class, it becomes a bit more complicated. But if you're writing both, you have the power to control where you're defining these things. Okay. Now, you can handle instantiation in parents and children, right? So this is one of those interesting things. So if I have a child class that doesn't have an init method, I can use the init method from the parent, right? So I can init my child with the parent, and it works. And it also works the other way around, which is you know, not surprising, because again, we're just dealing with the same hierarchical structure, right? So if I define the init in the child and the show in the parent, it works. Okay, because again, all it's going to do is look at the first dictionary that it can find to see if it finds the method it's looking for. If not, it'll go to the next dictionary and so on and so forth. And it only raises an error after it gets to the end of the chain and doesn't find what it's looking for. Okay, so now, what if you have an init in both? Right, now this is a much more likely example, because this is not necessarily a case of overriding, right? So this is a case that you might need to initialize both the child and the parent to do different things. Okay, so if you don't do anything, you're going to simply get the child initialization and not the parent one, right? So if we try to get the parent value, it won't work. But we can deal with this by instantiating the parent as well during the instantiation of the child. So if we define, again, a parent class with an init method and a child class with an init method, the child init method can call the parent init method when you create the instance. So I create an instance of child. It's going to call this init method. It's going to set this value. And then it's going to call the init method of the parent and set this value. And then you will see that the child now has, the child instance has access to both parameters. Okay. So in this particular example, we were very explicit. We use the exact name of the parent class that we wanted to instantiate. But Python has a magical super function, which is pretty aptly named, which basically allows you to automatically instantiate the parent, whatever it happens to be called. So I have, again, the same example, parent class, child class, same parameters, cval, pval, and instead of writing parent.init, I'm just going to write SuperInit. And you see that it works. Now, we'll come back to this in a second to understand how this is exactly working. But effectively, what it's doing is saying, looking at the bases that belong to that child and instantiating whatever the first base is in that list. Okay? So that's pretty cool, because then essentially what that would allow us in this particular example is if we decided we wanted to change the name of this parent class, we don't have to redefine anything in the child, right? Except for the class that it inherits from. So I could change this to, you know, from parent to mother, and I just change this to mother, and everything's updated. I don't have to redefine a lot of things, which can be really messy if you have a really big code. Okay, so you do have to be careful, because you could have multiple parents, right? As most children tend to. Right, so you could have a mother class with its own init method, a father class with its own init method, a child class with its own init method, and it wants to instantiate both parents. Okay, we can see that that works. Everything's fine, that's pretty cool. But what about that fancy super function we saw? Well, now things start getting complicated, because, of course, if I call the super method, who's getting instantiated? Right, now that's where things start to get messy. And we can see, oops, that we're going to get an error. And that's because the mother was instantiated and the father wasn't. All right. And the reason for that has to do with a topic called method resolution order. So I don't really expect anyone to remember this from today, but it's worth knowing about. So method resolution order is the order, and essentially the hierarchical order in which Python looks through the parents if there are multiple parents. So if you have a child class that inherits from 10 different parents, multi-resolution order will be like a list of all of those parents, and the order of that list will tell you the hierarchy of which one goes first in the inheritance. So you can actually look at the MRO for any given class. So if I look at my child's MRO, you can see that I have myself, the child first, then mother, then father. So the super method was going to instantiate mother, right? So if I wanted to instantiate both of those methods using superclass, and I just put a huge note here, don't do this. This is just for explanation purposes. If you wanted to understand how this is really working behind the scenes, this is how you could do it, but you shouldn't do it. So the previous example where I explicitly instantiated both parents would be the right way to do this in this case, because otherwise you have a lot of ambiguity, right? Super is great if you have one parent and you want to instantiate that automatically because it's very explicit, right? Because you know what the parent is, then you don't need to care what the name of the parent is, it's fine. If you have multiple parents, it becomes ambiguous who you're trying to instantiate, and you shouldn't add any ambiguity into your code. But that being said, let me just show you how it could be done now that you understand what the method resolution order is and how it works. So we have the same example from before. We have our child, both our parents inherited. We're passing some variables. We're running the super method here, which we know instantiates the mother. Well, then the mother instantiates the father using another super method there, which would instantiate this class, right? So we can see that in fact does work, but don't do it. Never do this, because that would become a complete mess, because somebody would have to know the method resolution order of all of your classes in order to follow the logic of all of the super methods in this chain in order to make that work. Now, I just wanted to show you this because it is possible and it does work, right? You can make these things work if you absolutely have to, but again, don't do it. Okay, and ambiguity is the key word here. Okay, is everybody happy with how inheritance works? At least roughly speaking? Yeah? Usually, yeah. Well, you'd have to check the method resolution order. That's why they have a method resolution order, because, like, I mean, the thing is, it can get incredibly complicated. Of course, the more classes that you inherit from, and the more hierarchical inheritance you have from each of those classes, it can be very complicated. And that's why there is a method resolution order, because at some point, if you say every single one of these classes defines the value x equals to something, and when you call your child and you say, show me x, figuring out where x is coming from can be extremely complicated, right? And that's why overriding is bad, right? Because specifically for that reason, because you can work out the method resolution order to figure out exactly the chain on which this hierarchy is, each one of these values is overridden, but you shouldn't have to. And that's the kind of the point. Okay, so now we're going to talk about a slightly related topic. I would say that this is less well known. This is in Python, it's called compositions. Anyone heard of this before? Okay. So this is something that I'm a huge fan of. So I wrote the whole package in Python based on class composition, and because I think it's incredibly cool. But you have to appreciate how inheritance works to appreciate why composition is a useful thing. Okay, so what's the difference? Right. So firstly, inheritance is extremely explicit in the sense that I define a child class and a parent class, and I tell my child what parent it's inheriting from, right? So basically, it's hard-coded into my child who its parents are, like real child. In composition, you have a bit more flexibility because essentially we're not hard-coding anything. So I'm going to define a class, which I call composer. It could be called anything, and it has an init method and an attribute, just like a normal class. I have a second class, a normal class as well. It's not inheriting anything. It has its own init method, and it has an attribute that I just happen to call comp, which is an instance of this composer class. So basically, as I instantiate this class, I'm creating an object, which is an instance of another class. Okay? So basically, creating my instance, calling comp.myAttribute gives me my attribute, right? So essentially, I have to know that the class that I have composed has this attribute in order for this to work, right? But what this allows you to do is to pass any class you want as a composer to this class. So rather than like a child, this could be like an adopted parent, right? It could be anybody who chooses to give you attributes rather than the one that you inherited them genetically from. So let's have a look at an example. All right, so imagine we have a class called star. It has a single attribute, which just tells you who it is, and then tells you it's a star. I have another one for galaxy. It tells you that it's a galaxy. And then I have my base level class, which is going to take an argument, which is a composer, which could be any composer it wants. And it's going to create an instance of that composer as we saw before. So I have an instance of this class where I pass star as an argument. So the class star, and another one where I pass the class galaxy. So it's almost like having an inheritance at the instantiation level rather than at the definition level, right? And you can see that works, provided, again, that both of these methods contain the attribute who am I. Okay, is that clear so far? Okay, so let's take this a little bit further. Let's say that I already know that my composer is supposed to have the attribute who am I, right? So rather than looking for the attribute who am I can predefine my base class with the attribute who am I, given the composer class's attribute who am I. So essentially then I do the exact same thing, but now I don't have to have any intermediate step. I can just say, okay, who am I? And based on how the class has been composed, it will have the appropriate value. Okay. Okay, so now, let's say we want to pass some arguments to these classes. So instead of just saying who it is, we're going to pass magnitude to the star or magnitude to the galaxy. And now my base class, I also want to have a magnitude, which is based on the composer class. Okay, so this example is important. So let's pay attention. So firstly, I'm going to create an instance of star. So I create an instance of star with a magnitude of 11.05. Then I'm creating an instance of my base class with the star as a composer, right? So this is a pre-instantiated class, so it's an instance of the class star, not the class star itself, that is being passed as an argument to my class. And then the same here, except that I'm not doing an external step. I'm creating an instance of galaxy directly in this call, all right? So then you can see, okay, in both cases, I get the correct magnitude, right? 11.05 or 8.2. But let's see what happens if I changed the instance magnitude or the instance composer magnitude, right? So if I look at the instance magnitude now, you can see that I have 12.3 as defined. And if I change the instance comp magnitude and I look at the star magnitude, so this instance that I created at the beginning, you can see that the value has been modified. And so what's happening in these compositions is that if I pass a pre-instantiated class, so an instance of a class object, as an attribute to a new class, it's a pointer to that existing instance, right? So if I change that attribute inside my class, it changes that attribute everywhere, right? So basically, I'm not doing anything with my base class dictionary. I'm literally just pointing to my composer class's dictionary. So all of this is doing is letting my base class say, okay, I want this attribute. I'm not going to bother storing it in my own dictionary. Well, I am sort of, but basically all I'm doing is storing a pointer to another dictionary in another class. And if I change that value changes over there as well. Now this is kind of hard for me to demonstrate in a simple example like this, how this can be extremely useful. But when you're doing things that require iteration or require looking for convergence in certain methods, having a method that you can pre-compose that looks for certain properties and allows your class to point back to those properties and then modify them iteratively can be extremely useful. So I can imagine, yeah.
I don't understand how this is different from if you just take the Init NumPy array.
Yeah.
This is already a configuration.
Yes, in effect, yes, right? So, but the thing is, the main thing is, if you think about this, is in the terms of classes that you've written yourself, right? So the main difference is that if you inherit the properties from a class, all you're doing is adding a hierarchy in the dictionary lookup for a given attribute. If you're composing, you're adding a pointer to an external class that you can co-modify between that instance and the actual class. So imagine you have some iterative scheme inside your class and you have some variable defined outside. You can modify that existing variable. So again, so like I said, it's hard for me to give you a very concrete example in like a few lines of Python where this is useful. But it's important to know what people mean when they say class composition and how it works, right? So the main thing is that you should not fool yourself into thinking that by passing this instance to your class as an object, that's a copy or a new instance. It's a pointer to the existing instance. Now that's good and bad depending on what you want to do, right? If you wanted a copy, then you've done the wrong thing. If you want to be able to interact with that existing instance, then you've done exactly the right thing, right? So the thing is that the composition gives you more flexibility in what you can do. And like I said, you can also have inherited properties from an infinite number of classes that you don't have to hardwire into your class. But you have to control the attributes that those have. And that's what we're going to talk about next. Okay, so this is the last topic for today. And then I can leave the rest of the time for exercises. And this is the highest level of complexity that we'll get to today. So if you can follow this, then you're pretty much on your way to being a Python expert. Okay, so abstract methods, right? So basically for this, we're using this special library called ABC. We're going to import a parent class called ABC capital letters. And we're going to import a decorator called abstract method. Okay, so then we're going to define a parent class the same way we were doing in the examples of inheritance called parent. The parent itself is inheriting this special ABC parent that we're not going to go into a lot of detail about. Then we're going to define a method. In this case, it's called getID, and we're going to pass this decorator abstract method. Okay, so if we look at the dictionary for this, I think, yeah, we can see here that we have in our abstract methods getID. Okay, so far, nothing particularly difficult to implement, but you're probably wondering what the benefit of doing this is. Okay, so now we're going to define a child class that inherits from this parent. It's going to have an attribute called who am I. And now I want to create an instance of this child, right? As you would expect on any normal thing. And we see that we get an error. And the error is explicitly telling us that the method getID hasn't been defined. Right? So what we're doing is basically adding some rules to the parent class that impose upon the child class. So it's basically saying, okay, if you want to inherit from me, you have to define this property, otherwise you cannot create an instance. Right now, if you think about what we were just talking about with the class composition, you can start to see how this might be useful. Like if I want to compose a class that, use a class that composes other classes that have certain attributes, and I want to ensure that I have access to those attributes, I can impose some properties upon them that forces them to have the right attributes before creating the instances. Okay, so let's have a quick look. Yes, in the child class. So, yeah, so basically what we do when we define an abstract class, we deliberately define an abstract class that has no properties. And basically all it does is it tells the child class that you have to override me, otherwise you can't instantiate. Okay, so now, yeah, here we go with example. So this time we're going to create a new child inheriting from the same parents. But this time we're going to define that getID as requested, and everything's fine. So you've seen as soon as we override getID, we are satisfying the parent and allowed to create an instance. Okay, so this doesn't just work for methods. We can also do this for properties. So you remember when we were talking about properties, we were talking about these getter and setter methods, and that we can impose conditions on what the getting and setting of certain properties does. Well, we can actually create abstract versions of these getters and setters. So we can, for example, set that this property, who am I, is an abstract method, but it's also a property.
Sorry, this abstract, this ABC thing is from the default.
Yeah, it's included in native Python, but you have to import it. Okay, yeah, so basically this is exactly the same as we saw before with the getter and the setter, but now that this is an abstract getter and this is an abstract setter, right? So you can see that neither of them are doing anything, and we're just creating a generic class called Astro Objects, which inherits from ABC, of course. So now we can define a child class called star that inherits from Astro Object, and it wants to define who am I, and we can see that that's not good enough. What we need to do is tell this child that it has to define a getter and setter for this property in order to be able to create an instance. So if we define the getter and setter according to what the abstract parent requires, you can see that it works. So now what we can really do is impose from the parent the properties that the child has to have, right? So then you can start to think about, okay, now I can create generic parent classes that force users to create children in the way that I want them to, right? So then basically what this is, if you want to think about this from a developer point of view, is kind of control from the back end to the front end, right? So you at the back end create the parent, and then the person working on the front end is forced to create a child that adheres to the strict rules that you've imposed with these abstract methods. So again, I would say that if this is your first time writing a class, you're probably not going to be writing an abstract class. You're probably not going to be writing any parent class or anything like that. But if you get far enough down the line, you might start finding, okay, I do want to be able to use class composition. I want to have this flexibility, but I need to be able to control what the composers are able to do or not able to do. And I can start doing that from the back end using these abstract methods. Okay, so that is everything I wanted to talk to you about. So you are now free to work on the exercises.